Okay, well, let's think now of a cylindrical capacitor. We use the result for an infinite line charge. We assume the cylinders are long compared to the we assume the cylinders are long enough that their curved area is much greater than the area of their ends. Okay, and they don't really have closed ends, but if you do Gaussian surfaces, you got to have an end. So we have coaxial cylinder radii A1 and A2, A1 being less than A2. So it's like this. Looking at it from the end, you have radius A1, you have radius A2 out here. Now, we want to calculate the capacitance. Well, the capacitance is the charge on the capacitor divided by the voltage. The charge on the capacitor, remember when we use a capacitor, we simply transfer charge from one plate to the other. Now these plates are cylinders now. They wrap around on themselves. They're not flat plates, but that's okay. You can put the charge from this plate and move it around to this plate, or vice versa. Okay? So the plates are going to become oppositely charged. You're going to have a charge Q on one, let's say the inner plate, and minus Q on the outer plate. Now we're not assuming whether Q is positive or negative, so Q could be positive or negative, so you could have positive here and negative here, or negative here and positive here. It doesn't make any difference when you're calculating the capacitance. Okay. Now, from the fact that you charge this capacitor by transferring charge from initially uncharged inner cylinder to an initially uncharged outer cylinder, the charges have to be equal and opposite. So we can, again, let Q stand for the charge. Now we know the charge Q. If we know the length of the capacitor, then we know the charge per unit length. And we can draw a Gaussian surface at some distance r from the axis. In other words, a cylinder, as we discussed a minute ago. Draw that cylinder at a distance r from the axis. And that cylinder encloses the charge Q. Okay, it doesn't enclose the charge minus Q, it just encloses the charge Q because it's in between the two cylinders. Well, we know the charge per unit length, and here's the thing I was talking about writing out, thing I described by waving my hands over here, where you divide the flux by the area. Okay, so if we divide the flux through this surface by the area of the surface, well, what's the flux? It's 4 pi kq, because Q is the charge enclosed. And you divide by the curved area of the cylinder, assuming the ends don't contribute a significant amount of area. Okay, so you divide by the curved area, which is 2 pi RL. Again, the area you would get if you slice this thing and laid it open. It would have dimensions equal to the circumference times the length. You find that the electric field in between here and here at distance r is 2kq over r times L, which we can write as 2k lambda over r, where lambda is q over L, the charge per unit length, measured in coulombs per meter if you use SI units. Okay, so that's the electric field of a long cylinder. Okay, and it's also, you can shrink the long cylinder down to a line. It's also the expression for the field of a line charge. Now, for the cylinder, this only applies if R is between, well, for the inner cylinder, it only applies if R is bigger than A1. If R is less than A1, your cylinder, your Gaussian cylinder, isn't going to enclose any charge. There's no charge inside here. Okay? And for the cylindrical capacitor, if R happens to be bigger than A2, well, you're enclosing how much charge? Q plus negative Q, that's zero charge. There's zero net charge on the capacitor. You've separated charge between the plates, but there's zero net charge. So your Gaussian surface would be enclosing no charge, so you would have no field. So we see then that there's no field inside the inner cylinder. There's no field outside the outer cylinder. But between the cylinders, there's field 2 pi kq over RL, or 2 pi lambda over R. Okay, so now, what's the capacitance? Okay, we know what the charge is, it's Q. How do we get the voltage difference between here and here? Well, voltage, if you have a constant field, you just multiply the field by the distance and you get the voltage. That just goes back to our intuitive idea, which we hopefully have, that the voltage is just work per unit of charge. If you multiply the charge by the electric field, you get the force on the charge. Multiply that by the distance you move, you get the work on the charge. So if we know the force per unit charge, we multiply that by the distance, we get the work per unit charge. We have a varying force because of the varying electric field. The electric field falls off as R. So we have to do an integral. So we end up with this integral, 2kq over RL. And I'm using the Q over L instead of the lambda. Perfectly legitimate. And this integral you can easily verify. The 2k over L just comes out of the integral. That's all constant. And you're integrating then 1 over R dr from A1 to A2. And that gives you the natural log of A2 over A1. So it's a very straightforward integral. And hopefully an intuitively obvious thing to integrate here, okay? So, well, there's our voltage change. Our capacitance is Q over V. And the voltage between the two is this. Well, if we divide that out, we end up with L over 2K natural log of A2 over A1. Okay? In other words, we're just dividing Q by this. The Q's divide out. The 2K natural log of A2 over A1 stays in the denominator. The L being in the denominator, this expression flips up into the numerator, and there you have the capacitance.